Welcome to RISE Learning Machines seminars. I am Olof Mogren. I'm a machine learning researcher here at RISE. RISE is Sweden's public research institute, and this is our open weekly seminar on AI and machine learning. This particular seminar is organized in collaboration with Climate AI Nordics, a network of researchers working on utilizing AI to fight climate change and its effects. This meeting will be recorded. Let us know if you want to be removed from this recording before we put it on YouTube. And by the way, on YouTube, you can find a large collection of amazing talks that we've had in this series through the years. Today, I have the pleasure to introduce Abdul Shaamala, who is a PhD candidate at Queensland University of Technology. Abdul is specializing in urban planning, geospatial analysis, and AI-driven optimization of green infrastructure. A lot of this work is focused on urban cooling and mitigating heat islands and improving climate resilience. So the topic today is optimizing green infrastructure for climate resilient cities, AI-driven approaches to urban cooling. And with this said, I will hand over the word and the screen sharing to you, Abdul.
Thank you. Thank you, Olof, for the introduction. I will just share my screen. Yeah, hello, everyone. First, thank you, Olof, for the introduction. My name is Abdul Shaamala, PhD researcher at QUT University in Australia. I'm doing my PhD in the area of using AI to optimize green infrastructure for climate resilient cities. So as you know now, AI become essential part of all majors, including urban planning, which we are trying now to use the advantage of using AI to help planners to face the climate change. For today, in this presentation, first I will start with a background about the optimization and green infrastructure benefits and why we optimize the green infrastructure. And then we will go through how we use AI for optimizing the green infrastructure. And then there is one of these cases, we applied it by optimize 3 location for improving the microclimate. And the last thing that we will go through, how we use AI to develop a model for help us to map the urban heat. So first, what is optimization? Most of you are coming from technical, maybe technical part of AI, but in general, optimization is finding the best solution of or outcomes among different options. Usually we represent this by maximizing or minimizing the maximizing the benefits or minimizing the effects. And we do this with certain criteria, and we define certain constraints for this optimization. Here there is an example can explain what optimization means and how it works. In this image, this kid, he's saying for his mother that he think he can find his way to the top of the hill. And this is how he defined his objective. And this is how we do it with optimization. So the mother gave him constraints that you can do this. You can try to find the top, but you have to be inside this fence. So she gave him constraints for his solution to find or to achieve his objectives. And this is the simple way to explaining what optimization means. Moving to the green infrastructure that refers to the network of natural and semi-natural areas, features, and green spaces that work together to provide ecosystem services. For green infrastructure, that could include trees, green spaces, parks, wetlands, forest, and sometimes things that related to a water system that could be included with green infrastructure. Here in our research, we're focusing on the green infrastructure side of parks, trees, and forest. And then in our case study, we will focus on trees as type of green infrastructure. And as you know, the benefits of green infrastructure can be extensive. These benefits including, but not limited to, improving air quality, enhancing the biodiversity. Also, it's improving the water system management, and mitigation urban heat, also for the economic benefits. And this benefits can come in themes of social, economic, and environment. So we have here extensive benefits of green infrastructure, but we have a question here. Is the benefits of green infrastructure equal? I mean, if we have 2 parks in one city, do we get the same benefits from these 2 parks? Or if there is 2 trees in the same street, do we get the same benefits from these two trees? The answer is no. Where there is some factors that affect of the benefits that we get from this green infrastructure. These factors could be the type, so the type of tree, type of park, also the size, and the location. These 3 factors shape the impact of green infrastructure. So from this point, the idea of optimizing green infrastructure started. So if we can get more from this tree, or if we can get more from park, why don't we optimize it? So from this idea, the optimizing of green infrastructure, because before that, the idea of green infrastructure was that it has the same benefits. So if we plant tree and the area A, it's equal to the benefits if we plant the tree in the area B. But after studying, find that all these factors could affect, and optimizing the location, size, and type of this green infrastructure can improve the benefits that we get from green infrastructure. So why and when and how we optimize the green infrastructure? So why we optimize, as we mentioned, to maximize the benefit of green infrastructure. So this tree will improve the urban heat in this location, but if we move it and change the type, that could be maximize the benefits. And this is why we do the optimization for green infrastructure. When we do this in the basic stage of urban planning, because it's planning, it's one of the basic or of the strategic stages of urban planning. And how we do this by adopt a comprehensive approach, consider the environmental, social, and economic context. So we do this optimization as to maximize the benefits, and it should be one of the early stages of the planning. From here, I'll share with you this literature review. So in this literature review already published in Sustainable Cities and Societies, it studied the research that have been done on optimizing green infrastructure to tackle the climate change. So for this research, the research question was, what aspects of green infrastructure need to be considered on the optimization process? So when we do the optimization, what the aspects that we need to consider. So these aspects should be like either objectives or could be indicators that will help us to achieve better results. And how do we implement the process of optimization? So if we want to optimize green infrastructure, what steps we have to follow? So these two questions were the research question of this paper. We use systematic literature review following the Prisma code. And we start by doing keywords that including green infrastructure and green area, green spaces, landscape, because all of these keywords related to green infrastructure. And then we need to define the tool that's used for the optimization. So we used artificial intelligence, AI, machine learning, and deep learning or algorithms. So the process is optimization. These were the keywords for the research, and we end up with 58 articles that use machine learning for optimizing different type of green infrastructure. First, the results show the aspects of the optimization process. So there was 5 main aspects of the optimization process for green infrastructure. First one was the objective. So what is the objective of this optimization? Then what's the type of green infrastructure? As we mentioned, there is different type of green infrastructure. So in the optimization, we defined what type of green infrastructure we need to optimize. Then what is the scale of a study? We have different scale of the study as we will see. And then what indicators that affect the optimization process for optimizing this type of green infrastructure. And finally, what tool they use to optimize the green infrastructure. This was the 5 main indicators or aspects of the optimization process, and we will go through all of these and see what type and what tools and indicators we're using through the optimization. So the objectives, there was 6 main objectives to optimize green infrastructure. First one was water management. So we know that green infrastructure is good for the water management, including stormwater and for the flooding. So one of the optimization objective was water management. Also air quality. Some studies that optimize the green infrastructure to improve the air quality. Also, one of the other objectives was the enhance the biodiversity and saving the ecosystem. Also, one of the objectives that we find is to improve the public health. We know that parks, many studies that shows that parks improve the public health, not only in terms of air quality or heat, also in the mental health. So one of the objectives was to improve the public health. Also, they optimize the green infrastructure to save the energy. So around the house, if the cooling, like if they use tree to cool the area, so we use less air conditions and we save the energy by getting natural cooling. And the last one was the heat island. And we know that it's the best solution to face the heat island is by the green infrastructure. So by a shading that's coming from trees, also how the parks that reduce the heat of the land surface. So here was the 6 main objectives that used in these studies that we reviewed on our article. So the other aspect was what type of green infrastructure they used on the optimization process. There was different type of green infrastructure were used for the optimization, including trees, and these trees could be either trees on the street or in park or around the house. So some studies try to optimize either tree on park, so inside the park, how they shaping the trees, or on streets to reduce the noise, or maybe around the house to save the energy. So there was optimizing for trees. Also, there is residential green spaces. So either by green roofs, green walls, and garden. So there was one of these studies that optimized the green roofs to reduce the heat within a city. So which roofs we use to plant so we can reduce the heat in the study. In bigger scale, there was urban green spaces, including parks, open spaces, swallows. So these are in bigger spaces. These optimization were in city scale. And finally, the natural green spaces, and this one was in regional scale, including forest, grassland, and wetland. So the studies use this type of green infrastructure to be optimized either by the size, the type, or the location to achieve certain objectives. And after defining the green infrastructure, there was defining for three other aspects, including the indicators. So the indicators that affect the optimization, including indicators related to the green infrastructure itself. For example, the size or the type of a tree. Sometimes it could be how they merge two like how the space of parks could be work as an indicator. Also, there was indicators related to the objective. So if we optimize a tree location to reduce the heat, we have here indicator related to the objective. So they will measure the heat, and then with changing the location, this indicator will be changed. So they will define this indicator. And there is geospatial indicators, including like in houses. So there is area where it's allowed to plant trees, whereas there is area like restricted from planting. So these geospatial indicators are related to the area around the optimization. For the study scale, there was 4 scales. So some studies that study the optimization in scale of building, that could be including the trees or roofs or gardens around the houses. So it was the study in a building scale. Other studies use street scale. So it was a bigger study. So it used some trees, more trees. It could be small parks. And the bigger scale was district. So by district, it's within a neighborhood scale. There was where to define the best location for a park, so that will achieve different objectives. Could be for improving the air quality or reducing the heat, or could be for the public health. And the bigger scale was a city scale, where the study of here could be for forest, could be for grasslands, or could be for national park. So this is the scales of studies. And finally, what optimization tool? Most of studies, they use optimization algorithm as a part of the optimization process. And there is some studies that use machine learning models for the optimization process. So now we define the 5 aspects, the objectives, the type of green infrastructure, the indicators, scale, and the tools they use for the optimization. Then we develop a framework for the optimization process. regarding to the green infrastructure. If we want to optimize a green infrastructure, what step we have to follow? So this framework starts first by identifying the issue. What issue we face? Is it the heat? Is it the flooding? Or maybe the public health? Then based on this, we define our objective. It could be one or more than one objective. So the objectives that we define, the 6 objectives, including the air quality, biodiversity, and energy saving, public health, heat island, and water management. We could optimize a park location to improve the air quality, public health, and reducing the heat. So it could be one objective or more objectives, but more objective that will make the optimization process more complicated because we have to simulate each objectives, how it's improved by the process, by the optimization process. Then after defining the objective, we start by selecting what type of green infrastructure we will use. Are we optimizing using tree or residential green spaces or urban green spaces or nature? So here, after defining the objectives, we will define the type of green infrastructure, and it's related to the scale. So if we are working in building scale, for sure, our green infrastructure would be either tree or residential green spaces. So the scale and the green infrastructure, it's something that everyone control the other. So here we identify the scale. So we can start by identifying the scale, then identifying the green infrastructure, and we can do the opposite. Then we have to identify our indicators. What is the indicators? Are we trying to optimize by changing the height of trees? So using more or using longer trees, or are we optimizing the type of trees? So this indicator would be related to the green infrastructure, and then we will identify our indicators that's related to the objectives. So are we trying to increase the air quality, or are we going to trying to increase the public health by changing the scale of parks? And finally, we identify our geospatial indicators, including the area that surrounded our optimization green infrastructure. Finally, we select our model, could be machine learning model or optimization algorithm. Then we will go for the optimization process. So this is the basic framework. It's basic. It's showing how the process goes, but it doesn't show the complicated relationship between them. But it's like guiding how the process of optimization green infrastructure going. So from this paper, we could find some gaps that in the process of green infrastructure. It starts in the beginning as a area of research. So one of the gaps that there is limitation of traditional approaches. We cannot optimize a tree location by the traditional way because it requires a lot of modeling. So that would be we could improve by estimating, but we can do it with the scale of building, but it's impossible to do it with scale of neighborhood or a city. Also, there is no spatial tools that for optimizing green infrastructure. And here we have a potential of advanced techniques. We can use AI to optimize green infrastructure. So we have a gap of limitation, and we have potential of techniques that we can use, and there is no special tool for optimizing such green infrastructure for the scale of city or neighborhood. So we use the framework that we developed from the literature review to start shaping a tool for optimizing green infrastructure. So first we defined our objective, and our objective was to reduce the heat island. So that was the objective. And the green infrastructure type, we used trees. So we need to optimize the trees to reduce the heat. And a scale of district, this district could be a neighborhood, less than a neighborhood. So it's not a building, but it's not a city. So it could be from a street to a neighborhood. Then we select our indicators and we choose the optimization algorithm. This done on our paper that we already published in Urban Climate. We used optimization algorithm to optimize the tree location to reduce the and improve the to reduce the heat and improving the microclimate. The question was of this research how we can optimize the location of a tree using AI tools or optimization algorithm to improve the urban thermal comfort index in urban areas. So how we can use optimization algorithm to optimize the location of trees, and we come with outcome that improve the urban heat. So this is the research methodology. We start by identifying our geospatial indicators. So we did the optimization on urban bark. This urban bark, it's hypothetical bark, as we will go through the case study. So we define the urban bark size, what is constraints. So the constraints could be the size of the bark. Also, if it's real bark, we will have like the could be other trees, also a walkable area. So these will be constraints. We cannot plant trees there. And we defined initial tree locations, and then we start by optimization.
A question.
Then, yes.
Could there be other kinds of constraints? Could there be constraints like it's too expensive to plant a tree, or it's
Exactly. So one of the constraints could be the number of trees. So we have a budget of 5 trees. So we will try to maximize the benefits by only 5 trees. One of the studies that's trying to optimize the trees or the park to reduce the cost of the maintenance. So these could be constraints, and it could be objectives also. Then after identifying the constraints, the tree locations, and the size of the park, and here we defined eight trees on this location. And then we did microclimate simulation. So with each configuration of trees, there was simulation for the heat, and this keep going until we find the best location and best configuration of these 8 trees that will reduce the heat. So this is like a loop. It's going through the optimization algorithm until finding the best location and best configuration of these 8 trees. We used, so our objective was to minimizing the urban thermal comfort, and we used 3 different optimization algorithms: non-sorting genetic algorithm second, and particle swarm optimization, and ant colony optimization algorithm. We used the 3 different optimization to see how it's going with different algorithm. So this is the hypothetical bark we used. It was 50 square meters. including 8 trees. And by 8 trees, we define the number. And we didn't use 8 trees for a reason. It was like we try to make less number. So we see how it affects with the optimization, the location, and the type of a tree. We used young ash, 6 to 10 years, so it's still young. And the dimension of the tree, it will be 6-meter diameter, and the height will be 10-meter. So here we defined the location of each tree. This was the initial position of the trees, and that what will be the when we will compare with other results when we did the optimization. So we did the optimization, and here the performance of the optimization algorithm, the 3. We can see that with the initial one, it was here random, but we first did the simulation for the previous. We did the simulation for this position, and then we compare it with the result. So we start with random positions, and then the algorithm try to find the best locations. So with each iteration, the optimization algorithm do a configuration for the 8 trees. Then the 8 trees go to the simulation models and come with the results of the urban heat and give it to the optimization algorithm. Then the optimization algorithm do another configuration, and this loop going until we find the optimal or suboptimal. We find the optimal and compare it with the suboptimal solutions. We can see here the urban heat started from 37. And in urban heat, we have different scale from temperature. It's not temperature, it's including the humidity, the wind speed, and the radiation. So 37, it's including, it's indicate for hot weather. So when we did the optimization, we simulated on the weather of Brisbane on the hottest day of the year. So the initial was 73 index for the urban heat, and we can see with the iterations, the optimization, 3 of them, they improve the urban heat, and they minimize the value of urban heat. So from 37 to 36.8, it's not that big different, but with hypothetical small study, that it's good. It's also improved that with different configuration, we can change the urban heat within a park or within a neighborhood. So this is the configuration we get from the optimization algorithm. These are the optimal scenarios, each one that presented by different algorithm. We can see that it's totally different, but we can see that they try to cluster the trees, and also trying to, by clustering that, it maximize the shading. So here there is different scenarios that's better than the initial one. Then we did the, so here we're comparing the 3 optimization algorithm, optimal and suboptimal scenario used. So if we go to the non-sorting genetic algorithm here, we can see this here in the optimal scenario, how the trees try to break the hot wave. So this pink and red that present the highest temperature. So we can see how the optimization algorithm try to break the heat of the temperature, or the wave of the temperature, comparing to the suboptimal. Same here for the practical swarm optimization algorithm, how the distribution of trees that make the less high temperature while improving the temperature here. Also, we can tell from the optimization when it's go to the simulation model. It's also the simulation. It has the sun direction. So this also showing the sun direction, how the tree, the location was optimized to reduce the heat, including the direction of the sun. So if there was a building around the park, the optimization could try to work with the shading of the buildings and improve the urban heat. So here there is different scenarios, optimal and suboptimal for the three optimization algorithm, and how it improve the air temperature. And then we compared the factors. So these the four factors that we use it to calculate the urban heat index, including the humidity, the air temperature, the radiation, and the wind speed. And the red one that presents the initial scenario that we create where the trees were in the corners. And we can see here only almost the four factors. The optimization where the optimized location were improved by reducing the humidity, reducing the heat, also reducing the radiation. Here we can see the radiation. It's a bit different because the movement of the sun. So it could be different from time to time. And this how we use the optimization to reduce these four factors, and when we calculate them and find the urban heat. So from this paper, we find also we facing a gap. This gap, it could be by the when we use the optimization and we need to simulate each rotation, each configuration of trees, that takes ages. So for one scenario, it could take like around 10 minutes. And if we want to do like more than 200, that could take more than a week. The tools that here we can find it is either it's demand high performance computers. Some of them that also it take long time to simulation. For this one, each algorithm it take me around a week. Also, some of these tools, it's consider the tree as a physical shape. So for example, the ladybug here, it's considered the tree as a physical shape. So we know that the tree affect the heat with different factors. It's not only by working as a shading tool. So this creates a gap for a simulation model. Could be less demand for computational demand, and it takes less time, and it treats tree with the all factors that affect the heat. For that reason, we try to improve a model using unit model deep learning. So we think that if we start to develop that model, so we can map the urban heat. And using this model, it could improve the time. Also, it could improve the result in general. So the question was how we use unit to enhance accuracy and efficiency of urban heat mapping comparing to the traditional methods. So the training data were coming from Adelaide City. So we used high resolution thermal and spatial satellite images. So we trained the model using the satellite images and the spatial images. So the model can see how the morphology affect the heat. And by this one, we can see the methodology we use. So here we start by training the model using the heat map and the real image. So the model understand how this built from the how it's built from the morphology of the city, and also it gets the temperature from this image, and we get an output of predicted map. So instead of modeling this using softwares, we try to improve this unit model. The model was good in terms of results. It was doing each iteration within 30 seconds. So within 30 seconds, we can get a simulation for the urban heat. But this model is still in the beginning, so we're still facing some issues. Also, we need to improve it because we only here use maps, but the urban heat, it's including temperature, humidity, and other aspects like wind speed. So we're trying now to improve this model by adding these factor into the unit model. So here's some results from the our model units. So here the ground truth and the predicted map. We can see that it's showing good results in terms of mapping the urban heat, but it's still, as I said, not presenting the urban heat in terms of how we feel comfort and heat, because we need to add in other factors. So what's next on this model? We are trying, first, we are trying to increase the number of training samples. We are trying to use different cities because climate is different. So with more different cities, that will improve the model accuracy. Also, we are trying to doing mapping the heat on the night and the day. Also, we are trying to improve by using climate variables like air temperature and humidity. When we improve that model, the ultimate goal is to build the tree optimization tool. So this tool will be optimize the tree location to reduce the heat. So when we input a neighborhood, we define the area where it's allowed for the model to plant trees. We define the number of trees, type of trees. We can use different types, different type of trees where they present different shapes, and the model, the optimization algorithm will start to use to configure locations for this tree. It will go then through the units model where we're modeling the urban heat. Then this one also, it will be a loop until we find the optimal location for trees to achieve our objective, which is reducing the urban heat. So this is our final objective from the research. It's to trying to build this tree optimization tool. So then we can also add a different objective. It could be air quality, but the problem with these tools, it's not the building the tool. The issue it's with the modeling. So if we have like models that model the air quality and can easily integrate it with optimization would be good. But the problem with the modeling that it takes time, it's require sometimes it's not possible even to integrate it with optimization algorithm. So this would be the final output of my research. Here are some of the references that I used in my presentation. And thank you for your listening, and I'm happy to receive questions and comments. Thank you.
Thank you, Abdul. And please, if anyone has questions, just shout out. And while you think of your questions, I may start with a couple of my own. So for example, with the model, the unit model that you made to predict urban heat, you used, that's a supervised training. So you have a ground truth for your training data.
Yes.
And why is it not possible to use that ground truth in your optimization?
So when we train the model, we use the satellite images and the ground truth as a training data. So it's like when the model read that the satellite image heat and also read the ground truth, because the satellite images, it's only show heat. So it's like the temperature of the surfaces, while the ground truth showing the morphology, because it's the shape of the like when it's in central areas, green areas, that's effect on the surface, on the temperature. So we trying to use both to train the model. So we have like a model that's read the heat with the morphology, because if we need an accurate urban heat modeling, we need to model the city. So we put the building, we put the parks. So with this way, it's not perfect way, but at least we know where is the building, what type of surfaces we have, and how it affects the heat.
Okay, thank you. Have you come across in your research examples where people take into consideration geographical information, like I'm sure an optimization may result in a different solution when planting trees in Queensland as compared to planting trees in Sweden, for example.
Yes, exactly. Yeah, sure. This would be very, very different because when we plant trees, first we have type of trees. Also, we have if we're talking on planning, there is regulation for planting trees. Also, how trees affect the weather. It's different from a city to city. That's why in our model, we start in a basic that we used only one city to train. We are looking for data from different cities, from Europe, from cold, hot cities. So by this way, we can get the data to identify. So we can define the temperature of this area, and the model can read and forecast how this tree could affect the city and this certain climate.
Great, interesting. Do we have some other question from the audience?
Can I ask one question? So you were, towards the end, you were saying you would like to incorporate time and other weather data into this model. But those are time-dependent data. So how would you anticipate putting that in when right now this is a static one-to-one?
So yes, exactly. So in this stage, it's still like we use only images. There is no temperature, but when we train the model, we cannot train it for 365 days, but we will train it based on seasons. So we need to plant tree to reduce heat. So we have certain months where the heat hit the highest degree. So this is the benefit we get it from tree. We don't need the tree to work that much on winter. So we will try to focus around our objective. So we will train it based on the highest temperature. And if it's reduced with high temperature, that means we achieved the goal by reducing the heat.
Okay, so got it. So you will be looking at the climatology and not the exact weather, and then
Yes.
optimize based on it. Okay, makes sense.
Thank you.
Yeah.
Great. So if there are no final questions, then we'll say thank you for this interesting talk, Abdul. Welcome back next week. It's April 10th. We'll have Beiqi Liang, who's a signal processing engineer at Epidemic Sound in Stockholm. She works on music modeling and machine learning for sound, and it's going to be a talk about sound copyright. So welcome back next week, April 10th.
Thank you for having me.